Here we are today with lesson number 4. We're going to work on some applications for the next couple of days to wrap up our geometric vectors unit. So we're still working to perform operations on vectors. We've also added to this that students will solve contextual problems requiring the use of vectors, and students will develop mathematical models to solve problems. In this case, your models are diagrams. This first definition is mostly for those of you who have not taken a physics course. A force is something that either pushes or pulls an object in a specific direction, hence a force is a vector. Forces are measured in a unit called newtons and is marked by a capital N. So an example of a force is gravitational force, which can be calculated by multiplying the mass and acceleration due to gravity, represented by the vector g. Then we have two other definitions. These will be somewhat familiar to those of you who have taken physics, but you can see we use different phrases for this. So we're going to refer to the resultant force as the single force that can be used to represent the combination of forces on an object. You will know this from physics as the net force. Those words are essentially interchangeable, but they will be referred to as a resultant force in this course. We also have an equilibrium force. This is the force that, when applied, will oppose the resultant force and maintain a state of equilibrium for an object. So this means the equilibrium force will always be the opposite vector of the resultant, because they will need to create the zero vector when added together. So we'll go through a couple of examples here. So two forces of 25 newtons and 40 newtons act at an angle of 30 degrees to each other on the same object. We're going to determine the resultant force of these two forces. So we have 40 Newton force, and again, you're going to do this with a ruler. And at 25 Newton force, and they're acting at an angle of 30 degrees to each other. So there we have our position diagram. And now we want to do our vector diagram to actually show the addition. So as you know, we can take these two vectors and complete a parallelogram, or we can use the triangle. So here comes our vector diagram. So we have 40 newtons plus 25 newtons, and they form that 30-degree angle. And it creates our resultant vector. So we know the magnitudes of these guys, and we also know that this angle here will be 180 minus 30 degrees. So this will be 150 degrees. And we want to know what this resultant vector is here. So once again, we have an enclosed angle in two known sides. So we're going to make use of our cosine law. (40 squared plus 25 squared). Sorry, I really should zoom in so I don't have to write so big. Minus 2 times 40 times 25 times cosine of 150 degrees. So 1600 plus 625 minus 2 times 1,000, and the cosine of 150 degrees is negative root 3 over 2. So that gives us 1600 plus 625 plus 1000 root 3. So 2225 plus 1000 root 3. And because we're working in a context, we don't need a whole, or sorry, an exact value. We can do an approximate value. So take our calculator. And we're also going to take the square root, of course. Should give you approximately 62.9. So therefore, actually no, we can't finish yet. We still need to figure out what the angle is formed. So we want this angle here. So we'll call that theta. And we'll have to make use of our sine law. So sine theta, theta is opposite to 25. Equals sine 150 over 62.9. And when we plug that into our calculator, we will get approximately 11.5 degrees. So this means that it's going to form an 11.5 degree angle with the 40 Newton. And then we can figure out that from the 25 Newton, that would be a 18.5 degree angle with the 25 Newton force. So now we can actually safely write a therefore statement. Therefore, the resultant force is 62.9 newtons and forms an angle of 11.5 degrees with the 40 Newton force and of 18.5 degrees with the 25 Newton force. Sorry, that first example took a little longer to get written down than I expected. I'll try to get through this one a little quicker. So example 2, we're doing 2 parts. So is it possible for 3 forces of 15 newtons, 18 newtons, and 38 newtons to keep a system in a state of equilibrium? So what we're looking for here is the resultant 0, because then we wouldn't need an equilibrium force. So the question is this possible? So can we draw a triangle that has the sides 15, 18, and 38? Is that even possible to do? And you should be pretty convinced, hopefully not too, it wouldn't take too long to convince yourself that no, this is not actually possible. And this is failing something you probably have come across in your homework at this point. It's failing our triangle theorem. So if you have the addition of 2 vectors, in other words, something that forms a triangle, it has to be less than or equal to the sum of the 2 magnitudes. So in this case, this one will fail because it's definitely not less. A plus B in this case, 15 plus 18 is 33. So 38 is not less than or equal to 33, so it's not possible. The second one is possible, so we have 3, 5, and 7 that are in a state of equilibrium. What is the angle between the 2 smaller forces? So we're going to combine 3, 5, and 7. And of course, if you're drawing these to scale, they won't be too hard to do. 3, 5, and 7. And we want to know the angle between the 2 smaller ones. So 3 newtons, 5 newtons, 7 newtons. We want to know this angle here. And we know that adding these things together, so putting them all tail to tip, brings us back to the start. So the resultant would be 0. So we're going to use that information to find the angle. Here we have 3 known sides, and we're looking for an angle. So this is an opportunity for cosine law. So cosine of our angle, 3 squared plus 5 squared minus 7 squared over 2 times 3 times 5. So we're going to be taking the inverse cosine of 9 plus 25 minus 49. And you should be able to gather from our diagram that we should be looking for an obtuse angle here, which I can already see is making sense because the numerator is going to be negative, and a negative ratio will give me an obtuse angle for cosine. 2 times 3 times 5, so over 30. We're going to plug that into our calculator to see what we get. And if I'd thought ahead a little, I would have realized I didn't even need my calculator because the interior of this is negative 1/2. So it does in fact give you exactly 120 degrees. It's not even approximate. So we can conclude, therefore, the angle between 3 and 5 newtons is 120 degrees.